Hello folks, this is the second lecture in Photonic crystal series. It is based on two-dimensional photonic crystals. The previous one was on one-dimensional photonic crystals. So let us start. Two D photonic crystals, as the name suggests, has periodic variation of permittivity or refractive index in two dimensions. These are the photonic crystals examples of 2D photonic crystals. This one here is called dielectric vein type of structure. This is a dielectric rods in air holes in a dielectric, and a different type of air holes in a dielectric structure. This one has square array, square lattice, and this one has hexagonal lattice of air holes. These are the most common type of photonic crystals. Now, before getting into the details of 2D photonic crystals, first let us understand nomenclature of polarization as TE and TM, transverse electric and transverse magnetic. Transverse electric and transverse magnetic, in case of rectangular waveguides, goes like this. Let's suppose a light is propagating along the length of this waveguide, and in this entire process, if electric field remains normal to the direction of propagation all the time and has no component in the direction of propagation, it is called TE polarization. And if the propagation is happening in such a way that magnetic field is always normal to the direction of propagation and has no component of it in the direction of propagation during this entire flow of energy, it is called transverse magnetic or TM polarization. This is what it is like in case of rectangular waveguides. In case of photonic crystals, the situation is different. The convention that has been accepted by photonic crystal community all over the world goes like this: that if the electric field is normal to the direction of propagation, or to be more precise, the plane of propagation, as light is launched into this photonic crystal, it spreads in the plane of this photonic crystal. So if as the light spreads in this plane, if the electric field remains normal to the this plane all the time, remains normal to its propagation, it is called TM mode. And this is absolutely contrast to the previous case of rectangular waveguides, that electric field is remaining normal all the time to the propagation of direction of propagation, and it is being called transverse magnetic. Similarly, if magnetic field is normal to the direction of propagation or to the plane of propagation, it is called transverse electric. This is the reverse convention that is used in case of photonic crystal then in case of rectangular waveguides. Before diving into the photonic crystals, let us take a look at the 2D Brillouine zone. On the left, you can see that this is a square lattice, an example of a square lattice, and its corresponding square Brillouine zone. The Brillouine zone also here contains an irreducible Brillouine zone. The irreducible Brillouine zone is that region which can be operated by mirror and rotational symmetry to generate the complete Brillouine zone. So it is sufficient to analyze this region of Brillouine zone only, and understanding this will help us understand the entire Brillouine zone. So irreducible Brillouine zone is labeled at three corners as gamma, chi and m. Gamma points corresponds to zero wave vector. Chi point corresponds to the wave vector having x component only, equal to pi by a, and m corresponds to the wave vector having both components x and y, each component is equal to pi by a. Looking at the band structure, we see that these two are the band structures of one-dimensional and 2D photonic crystals, 1D and 2D photonic crystals. These band structures are obtained by solving this master equation. This is an eigenvalue equation. If it is solved for different values of k, different value vector, it generate these curves, these curves for eigenfrequencies at different k's at different wave vectors. This x-axis here represents the values of k in the one-dimensional Brillouine zone of a one-dimensional photonic crystal. If same type of structure is to be obtained for a 2D photonic crystal, the Brillouine zone is going to be 2D. This plot here has a 2D Brillouine zone, and the analogous to the dispersion curves here, dispersion surfaces are being obtained for the two-dimensional case. Since it is two-dimensional, it has both components of wave vector kx and ky, and the corresponding dispersion surfaces are obtained, which gives the value of frequency for a particular kx and ky pair. We see that the band structure is completely different for a two-dimensional Brillouine zone, but that type of band structure is computationally rigorous. It creates a lot of burden on the computational resources, and sometimes it is not necessary to compute that much. So what we do is we only perform computation in the irreducible Brillouine zone region, that too at its boundary. This is the band structure for a 2D photonic crystal of a square lattice of dielectric rods. So it does not look like this. It looks more like this, but does not have symmetric curves like this. It is of a 2D band structure but does not have dispersion surfaces. It has dispersion curves. Why we are doing this? Because we don't need to compute in this entire region or the entire Brillouine zone. Only computation along the zone boundary, the boundary of the Brillouine zone is irreducible Brillouine zone, is sufficient. This is the case because maxima and minima in the band structure in any band occurs at the almost all the time, almost always it occurs at the zone boundary. Just like in this case, the maximum is appearing at this point, which is at the zone boundary at the corner M, and minimum of second band is appearing at this point, which is at the zone boundary at point chi. So almost always the maximum and minima of the bands occur at the zone boundaries and zone corners. So this is why it is not required to perform computation in the entire Brillouine zone. Only the periphery of the irreducible Brillouine zone is sufficient to be analyzed. So this is the band structure that we obtain for a square array of dielectric rods for both TM and TE polarization. Now let us have a look at the typical photonic crystal structures, two-dimensional photonic crystal structures. This is the most common dielectric rods in air. Band structure has been computed for it for both the modes TE and TM. This band structure has been computed for these parameters: the epsilon, the high dielectric region, the epsilon of rods is 8.9, which is same as that for alumina. These has been considered to be alumina rods erected in air. So the surrounding medium is air. The radius of the rods is 0.2 times the periodicity. Periodicity is the separation between two neighboring rods is the periodicity, so which is represented by A. So 0.2 times A is equal to R. R is the radius of each rod. So radius of each rod is 0.2 times the periodicity. Now what do you observe in this? We see that the TM modes have substantial band gap of 31%. the TM mode, you can see there is a substantial gap between the first band and the second band. But for T mode there is no gap between any band, so you do not see any gaps in T modes, but there is 31.4% gap for TM mode. What is the advantage of this type of structure? Is that the advantage is it can be used as polarization filter. If we allow a frequency lying in the gap region of TM polarization to pass through it, it will not pass through, it will be blocked, it will be stopped. But if that frequency has polarization of T is of T polarization, it will be allowed to pass through. So a frequency of this region, if it is of TM polarization, it will be stopped. If it is of if it is of T polarization, it will be allowed, and if it is of TM polarization, it will be stopped. So in this way we can separate out T polarization from TM polarization. This is why it is called polarization filter. Now let us look at the field plots in this dielectric rod type of photonic crystal obtained at these three special points of the irreducible Brillouine zone. You can see that the first pair is for band 1 and band 2, the dielectric band and the air band, at gamma point. At this gamma point is the center of the Brillouine zone, and you can see the field is same in the each unit cell. It is same throughout. Now before understanding this, we must first understand that the color contour is like this, that blue color indicates negative polarity, and red color indicates positive polarity, and white region indicates nodes. So you can see that band 1 has negative field, negative dz. It is the displacement field, the negative displacement field in the rods, while band 2 indicates the fields for band 2 has positive polarity inside the rods. At gamma point, at x point or chi point, you can see that this is a wave like sinusoidal type of variation. One entire row is blue, is has negative polarity of dz field. Next has positive polarity, then blue, negative polarity. The alternative polarity is seen like a sine wave, like a wave like pattern. This happens in case of band 1. In case of band 2, you see that there is a node line passing through the rods. Now, as we already know that band 1 or the dielectric band has more tendency to concentrate energy or field inside high dielectric regions. So this is what we are seeing here. The fields are more concentrated in the rods. But in this case, there is also a nodal line passing through the rods. So the concentration of fields inside the high dielectric region will be lesser for band 2 compared to band 1. And similar is the case with M point. You can see that in M point for band 1, the field is concentrated inside the rods more compared to the band 2. In band 2, the node lines are passing through the rods, so field is spilling into the air region also to a great extent. The difference, however, is that for gamma point, the field is seem to be varying along x direction, but in this case the variation is along diagonal. It is a checkerboard like pattern. This type of pattern is being obtained because remember that M point corresponds to the both the components of wave vector. It has x component as well as y component. However, chi point or x point corresponds to the situation when wave vector has only x component. So the previous one was the field plot for TM mode in case of dielectric rods. All these plots are for TM modes. Let us look at the plots for TE mode. For TE mode, however, instead of DZ, we have HZ plots. because it is T mode. In T mode the electric field is in the plane and magnetic field is out of the plane. So this is why the is along the z direction it is magnetic field which is along the z direction. This is why we have got hz plots over here. From now in this hz plot you see, and you can see these white regions passing through the dielectric rods in case of band 1, and white regions are passing through the airspace in case of band 2. This field contour plot, or this color contour plot, is for H field, not for D field. D field is obtained by paying attention at the nodes of the H field. If you see, you can see that these white regions are the nodes of the H field, and the locations of the nodes of the H field is the location of maximum in the D field. So you can see that D field in this case is passing through the rods in case of band 1, and D field in case of band 2 is present in the air region. So that means that more electric field energy is present inside the dielectric region in case of band 1, but most of the electric field energy is present in the air region in case of band 2. So this is why, and we already know that it is obviously called the dielectric band, and this band is obviously called the air band. Now what do we understand from it, and what is its consequence? To understand the consequence, there is a quantitative factor, the quantitative term called concentration factor, which tells us about the amount of electric field confined in the dielectric region of the photonic crystal unit cell. It tells us about the percentage of energy, electric field energy, which is confined in the high epsilon region. Now you can see that if you compare the concentration factors for the two types of polarization for two bands, band 1 and band 2, you see these values. These values have been obtained from this formula. In this formula, the denominator represents the energy density in the entire unit cell, and the numerator represents the energy density in the high dielectric region. Now you can see that for TM mode, the band 1 or dielectric band has 83% of concentration factor. That means 83% of its energy is confined in the dielectric region. But a air band, for band 2, the TM polarization has only 32% of its energy confined in the high dielectric region. So this is a huge difference between the concentration factors of air band and the dielectric band. Dielectric band confines most of its energy in the high dielectric region, but air band confines most of its energy in the air region. This is the reason between the huge frequency difference also between these two bands in TM polarization. As the result, it has a substantial amount of band gap between the band 1 and band 2. However, for TE polarization, the situation is different. In TE polarization, you can see that electric field is, though the D field is passing through the high dielectric region in case of band 1, and it is mostly present in the air region in band 2, but still the difference between the concentration factor is not significant. Only the 20% is the concentration factor for dielectric band. It is not the difference is not much. So this is why the difference in the frequencies of the band 1 and band 2 are not significant either. Hence there is no band gap. Now why is it that the dielectric band for TM mode has this much concentration factor, but for TE mode has only this much concentration factor? The answer lies in the next slide. You see that TM polarization has this type of field orientation with respect to the rod, and T polarization has this type of field orientation with respect to it. Now you can see that in this type of orientation, uh, you can see that electric field acts as is the tangential to the boundary of high and low dielectric region, and in this case electric field is normal to the boundary of high and low dielectric region. It is normal, and we know the tangential component of electric field is continuous and normal component of electric field is discontinuous. So tangential component of electric field is continuous in this case, and normal component of electric field is discontinuous, and normal component of D field is however continuous. So keep this thing in mind, that tangential component of electric field is continuous and normal component of displacement field is continuous. Now why these two polarizations have different concentration factors in case of dielectric bands? The reason is that if you look at this formula is for the energy density. Now from this formula, if you apply this formula for the TM mode, you see that electric field is tangential here in TM mode case, so it is continuous throughout. Electric field inside the rod is same as electric field outside, but epsilon is not same. Epsilon outside is less, so energy density for TM mode inside the rod is greater than the energy density outside the rod. Similarly, if you consider the TE polarization, in case of TE polarization, we know that D field is continuous. So if D field is same throughout, if we move out of the rod, we see that epsilon is less outside the rod and epsilon is more inside the rod. So energy density is greater outside the rod and lesser inside the rod. So obviously you can now understand that for TM polarization, the energy density inside the rod, inside the dielectric region is more. This is why greater concentration factor for TM mode, and energy density inside the rod is less for TE mode. This is why lesser concentration factor, and for air band it is obvious that concentration factor is going to be less, because air band has this tendency of concentrating more of its energy in the air region. So this is why it is obvious that air band will have less concentration factor, but the dielectric bands of these two polarization have different concentration factor because of this region. So it seems obvious that there is going to be a contrast between the concentration factors of dielectric band and air band in case of TM mode, but contrast is not going to be significant between the dielectric band and air band of TE mode. Now let us talk about a different type of photonic crystal. This is a square lattice of dielectric vanes. Dielectric vanes is a complementary type of structure to dielectric rods array of dielectric rods. It is complementary not only in the design but also in the behavior. In case of dielectric rods, we saw that the dielectric rods had band gap for TM mode but no band gap for TE mode. For this case, however, the situation is reverse. TE mode has 18.9% band gap, but TM mode has no band gap at all. This is the reason why we are calling it a complementary type of structure. Now, if you look at the concentration factor, in this case, in case of dielectric vanes, you see that TM mode has concentration factor of 89% in case of band 1 and 77% in case of band 2. the difference between air band and dielectric band's concentration factor is not significant in case of TM mode. So it is obvious that TM mode is not going to have any band gap. However, if you look at the TE mode has dielectric band concentration factor of 83% and air band concentration factor of 14%. The difference between these is huge. Because of this huge difference, it is obvious that TE mode is going to show a substantial amount of band gap. Just like the TM mode showed huge band gap in case of dielectric rods. Why this difference in the concentration factors, and why the air band has high concentration factor in case of TM mode? Let us see. If you look at the field plots, you see that in case of TM mode, for if you look at gamma point, you see that electric field or displacement field is confined inside the dielectric region. It is confined in the vertical columns, vertical veins, and in the cross region for band 1. However, in case of band 2, the vertical veins have a nodal line, a nodal region, but still the horizontal veins are providing for the confinement of the high dielectric. They are providing the high dielectric region for the confinement of DZ field. So in both the cases, despite the presence of a nodal region inside the dielectric inside the dielectric vein, still still there is a scope for the DZ field to be confined in the dielectric, because though in this case it is being confined in the vertical veins and the cross region, here it is getting confined in the horizontal veins. So dielectric region is still available for it. It is not that the most of its energy is being spilled into the air region. It still has a dielectric region available. So this is why there is not a huge concentration difference between these two bands. You can see that these two bands have similar, almost similar concentration factor. It is 77%, 89%. There is not much difference. The slight reduction is because of the nodal line present in this band. This is the reason for slight reduction, but this reduction is not substantial, is not sufficient to create a band gap. However, in case of TE mode, you can see that in case of TE mode, just like the previous case, we have plotted HZ field for TE mode instead of DZ field, because obviously it is HZ which is normal to the plane of propagation in this case. So we have plotted HZ field, and in this HZ field you see the white region which corresponds to the maxima of DZ field is lying inside the dielectric region. So that means DZ field for band 1 is confined, DZ field is confined inside the dielectric region. So electric field energy is concentrated in the dielectric region. This is why concentration factor is high for dielectric band. In case of band 1, the DZ field is present inside the dielectric veins. So obviously the electric field energy, that means, is confined in the dielectric region. More of electric field energy is concentrated in the dielectric region. So obviously the concentration factor for dielectric band is more. However, for the band 2, the field plot looks like this. HZ field looks like this. So, and this white region which indicates the distribution of DZ field, it can be seen to be present in the air region. It is though it is passing through the dielectric region for some time, but most of it is present in the air region. This is why DZ field is mostly lying in the air region. So lesser electric field energy is concentrated in the dielectric region. This is why concentration factor for TE mode, band 2 of the TE mode, is very less. So this is why there is a huge contrast between the concentration factors in case of TE mode, but there is not much difference between the concentration factors for TM mode. Now, after these two types of complementary structures, we have come to an entirely different type of structure, a third one, which is a periodic array, a hexagonal array of air columns drilled inside a dielectric slab. It is a hexagonal or a triangular lattice. Its unit cell looks like this. This red polygon is the unit cell of it. It has the periodic arrangement of of air columns drilled inside a dielectric slab, and it looks like this. Now, what is the advantage of this type of structure? We saw in the previous structures, we saw that rods one, the one which was made up of rods erected in air in a square array pattern, had band gap for TM mode only, and the dielectric vein structure had band gap for TE mode only. So only one type of polarization could provide band gap in in those two structures, in both the structures. Can we think of a structure which can provide band gap for both type of polarization, TE and TM? Answer is, if we are able to come up with a structure which has characteristics of both the previous structures, we can surely obtain band gap for both polarizations. Now let us look at the design specialty of the previous structures that we just studied. In dielectric rods case, there are isolated high dielectric regions, but in case of dielectric veins, it is a well connected structure. It is not like isolated dielectric region, it is a well connected structure. So if we can come up with something which is intermediate in between these two, it can have characteristics of both. So a triangular lattice is one such design. A triangular lattice of air columns is one such design. The one which looks like this. If we have the radius of these holes sufficiently large such that it gives rise to the appearance of this structure as if it is made up of isolated dielectric regions, but not completely isolated from each other. They are isolated dielectric regions, but they are connected through narrow channels of dielectric. You can see that in this structure, if the size of these holes are sufficiently large, you can see the most of the region is air, and only small separated high dielectric regions are there, but they are not completely isolated from each other because there is a thin channel of dielectric between them. They are connected as well as isolated to some extent. They are connected to some extent and isolated to some extent. They are not completely connected and they are not completely isolated either. So this is an intermediate type of structure. So this intermediate type of structure, if the band structure is calculated for it, it looks something like this. This band structure has been calculated for R by A of 0.48. Epsilon has been assumed to be 13, and you can see if the band diagram is computed for both polarization T and TM, you can see there is a significant band gap which exists for both of them. This type of band gap which exists for both T and TM polarization is called complete band gap, and it is obtained in this type of structure. It is a hexagonal lattice of air columns inside a dielectric slab, and this is how its Brillouine zone looks like. Since it is a hexagonal structure, its Brillouine zone is hexagonal as well. Now here is an animation of an interesting application of photonic crystals. You can see that the here I have designed a photonic crystal which is basically a square array of dielectric rods erected in air. And what I have done is I have removed one complete rod from the middle. I have removed this rod from the middle, and uh, I have allowed an EM wave to propagate in this defect region. When I removed these rods, I have created a line defect, and in this line defect I have allowed an EM wave to propagate. The frequency of the EM wave falls in the band gap region of this structure. So it is not so otherwise it is not allowed to propagate in this photonic crystal, but since I am making it propagate in the line defect region, it can propagate. And you can see that the light is able to propagate in the central channel, but it is not penetrating into the sides because it corresponds to the frequency of this EM wave is from the band gap region. This is why it is being stopped sideways, but is only able to propagate along the x direction. So this is all I had to tell you about two-dimensional photonic crystals. It is very interesting and a very useful device from the integrated optics point of view. If there were any typos or slip of tongue, please excuse me for that. Thank you very much. Have a nice day.